What if I told you that there's a road that has infinite size, zero length, and a fractional dimension? There's actually a logical explanation for this that lies within a very complex field of mathematics.
And these ideas are key in understanding the math behind fractals, the infinite geometrical patterns that dominate the world around us. We first have to take a look at something called the Cantor set. Imagine a roadway, let's call it Cantor Road, that stretches 1 kilometer inclusive of its endpoints. Now remove the middle third of the roadway, but not its endpoints at 1/3 of a kilometer and 2/3 of a kilometer. Now remove the middle thirds of both of those segments. If we take away the middle thirds forever and group the endpoints that you're left with, you have the Cantor set. You'll notice that after the first time a segment is removed, we have 2 endpoints. After that, we get 4, then 8, then 16, and so on. All of these endpoints lie on the road. We can keep removing segments, creating more and more endpoints, meaning the road is infinite in size. But how can something be infinite in size and have 0 length? Well, we know that our original roadway has a length of 1 kilometer. This means our next roadway has to be a third less than the first. The second roadway would have a length of 1 minus 1/3. The third, a length of 1 minus 1/3 minus 2/9, and so on. Using the infinite series formula, we find that all of the negative numbers added together equal -1, and 1 minus 1 is 0, which means the road would eventually have 0 length.
But how exactly does it have a fractional dimension?
If we look at a line segment, a one-dimensional shape, and triple its length, we end up with a line segment that's 3 times as long. If we take a square, a 2-dimensional shape, and triple the length of all the sides, we end up with a square that's 9 or 3 squared times as big as the original square. Notice how the exponent in each case corresponds with the dimension of that object. But our roadway is different. If we triple the distance of the road, we end up with a new roadway between 0 and 3 kilometers. Even though we tripled the length of the original roadway, we end up with only 2 new roads. Now let's put this into an equation. When we solve for d, we get 0.631. That is the dimension of Cantor Road, meaning the dimension is fractional. Fractals actually share the exact same property. Let's take a look at the most famous example of a fractal, the Sierpinski triangle. We can see that it has 3 identical segments. The smaller triangle has half the length and width of its larger counterpart, meaning the smaller triangle is scaled up by a factor of 2 to get the larger triangle. But like I mentioned earlier, there are 3 small triangles that make up the larger one. So we can say the larger triangle is 3 times the size of the smaller ones. If we simplify and solve for d, we know that the dimension of the Sierpinski triangle is about 1.58.
And this is why math is so amazing. It helps us to explain both complex and rare phenomena, while at the same time helping us to understand more simple things we observe every day.